All right, welcome back, everybody. We are on for our last reverse pitch of the day. This reverse pitch is going to be about decarbonization, demand response, and customer engagement. I'm going to pass it over to Jock. We have quite a large panel here to kick us off today. It's going to be a great session. Please feel free to post any questions or comments in the chat and Q&A. Just like previous sessions, we will be monitoring that, and we will answer them at the end, pending we have time left. All right, Jacques, over to you. Thank you.
Okay, thanks, Hannah. Hi, everyone. I hope everyone can hear me. So for the next 2 hours, we're going to be talking about decarbonization, demand response, customer engagement. So first in this session, we'll have two stories, one from the academic side, Priya Danti, and then we'll have one from the industry side, and we have a team from LA.DWP to talk to us about the real world there. The focus of this presentation session, just to sort of put everyone back on the same page, is to present data-related challenges and opportunities for using artificial intelligence and machine learning. And then I hope everyone will come back 30 minutes later for the breakout session, where we'll be thinking about key areas for collaboration and places where EPRI can issue grand challenges. So for this first hour, so essentially we're going to have two presentation slots. So first we're going to have Priya, and I'll introduce Priya just a bit more in a second for a first slot, and then we'll have I'll come back on to introduce the LA team, the LA.DWP team, who will go next for the next 20-25 minutes. So one thing I want to say to everyone who's listening to us right now, so there's a chat, so I can't see it, but the questions are being passed on to me. So so if there are questions at any time during the presentations, please please engage with us. Please type those in. Ideally, we would all be in person, but the chat is our replacement for the physical presence. So so please do engage with us. Send your questions. I won't necessarily stop the presenters as we're going along. I'll let them talk through their slides, but if we have time at the end of Priya, maybe we'll take one or two clarification questions. We'll do the same after the LA.DWP team's talk, and depending on time, we'll have a discussion in the end. So send us your questions and thoughts as we go through. Okay, so to start with Priya. So Priya is a PhD student in the Computer Science Department and the Department of Engineering and Public Policy at Carnegie Mellon. Priya is co-advised by Zico Coulter and Ines Azevedo. And I actually know one of Priya's co-advisors because Ines recently joined Stanford. So I've already heard about some of Priya's work through Ines. And Priya is also a co-founder and chair of Climate Change AI, a great initiative to try to catalyze work, bring in some expertise from machine learning to climate change relevant work. And so, in general, Priya's work is at the intersection of machine learning, electric power systems, climate change mitigation, and her research explores ways to incorporate domain knowledge, such as power system physics. That's one of the things she's going to talk about today, into machine learning models. So I guess with that, Priya, please go ahead and take it away.
Yeah, today I'm going to talk a little bit about sort of key methodological challenges that I think machine learning researchers and practitioners will need to contend with in order to make sure that their work is actually applicable in the real world, in power systems. So in particular, there are lots and lots of different places in the power sector where the use of machine learning has been proposed. So things ranging from electricity supply and demand forecasting to maximum power point tracking, trying to basically optimize how renewable generators are operating in order to maximize the amount of power they're producing, to predictive maintenance, to state estimation, to power system optimization, and so on and so forth. And so I'm not going to go through every single component of this figure, but I put it up here just to say there really are a lot of places where machine learning has been proposed. And I would sort of bundle these applications into two parts. One of which is applications where we already have really good machine learning methods that can already interface well. So these are things like with forecasting or with predictive maintenance, where both the methods are in a good place, and in general, these don't necessarily require tight integration with, for example, legacy software through power system optimization in a way such that these applications can be developed a little bit more separately from some of the other processes that go on in the power sector. So that's one set, sort of deployment-ready applications, both because the machine learning methods are there and because they're in some sense a little more decoupled from certain kinds of legacy software and operational processes. A little more. Obviously, it's more complicated than that. And on the other hand, I would say there's a class of applications like accelerating power system optimization, like robust and adaptive optimization, where these now fundamentally interact with existing power system optimization software, where it's really hard as a result to test these various methods out. And there are lots of ways in which machine learning methods today are not necessarily ready to be integrated into those workflows. So I'm going to focus on this second part, these applications where both there's difficulty in actually testing out methods on the ground and where the methods themselves need to evolve to an extent. And so in particular, on the machine learning method side, I would say there are three main foci that the machine learning community will need to contend with here. One of them is fidelity to physics and hard constraints. So, I mean, as we all know, of course, there are many different kinds of, physical equations that govern how the power system works. And if these aren't necessarily satisfied, for example, during a power system optimization run, then this can lead to, many kinds of difficulties, higher costs, blackouts, so on and so forth. And machine learning methods in general don't necessarily know about these constraints. They tend to take some data from the electric power system, analyze some patterns in it, spit out an answer, sort of naively unaware of the fact that these constraints exist. And so there's started to be some work that has tried to better bridge this machine learning and data story with this physical modeling and physical equation story. And so that's sort of one area that I'll chat about here. Another area of focus is sort of tighter integration with both humans in the loop in power system optimization processes, as well as regulatory requirements that govern these kinds of algorithms. So I'll get into this a little more, but this is where I'll sort of mention interpretability, uncertainty quantification, and other sorts of decision integration as being important in this context. And then a last one, which is a difficult one, is distribution shift. And when I say distribution here, I don't mean electricity distribution systems. What I mean is sort of the probability distribution that our data is drawn from, sort of the base reality of our underlying data. And so think about, for example, if we did demand forecasting before COVID-19 and demand forecasting after COVID-19, the sort of base reality has sort of shifted. The way in which we actually are seeing electricity consumption around the grid has changed. And so this is the question of distribution shift, which I'll again get into a little more later. So first, zooming into this question of fidelity to physics and hard constraints. So there are a number of different ways in which sort of machine learning and power system physics have been integrated together in the past. And I'm going to try to give a little bit of an overview of the ways in which this has been done so far, but sort of with this and with everything else I'll describe throughout this presentation, the idea that basically there's a lot more to be done in these areas, again, in order to better integrate machine learning into power systems workflows. So one way in which machine learning and physics have been bridged has been the use of machine learning within existing power system optimization models or engineering optimization models in order to make those models faster in some way. So for example, there's been some work in security constrained unit commitment that has tried to identify, okay, which constraints of this unit commitment problem are likely to not matter at a given time, and sort of learning from historical data when that might be the case. And then you can get rid of those constraints from security constrained unit commitment, make the overall problem a little bit smaller, and as a result, that problem is faster to run. Another way in which this has been done, in which machine learning and existing models have been integrated, is learning so-called warm start points in optimization solvers. So trying to figure out, can I create an initial guess for my solution to, for example, an AC optimal power flow solver or a unit commitment problem? Can I then give that initial guess to a traditional optimization solver and then have it, from that initial point, figure out the final solution? And can I choose that initial guess in a way that makes that overall solution procedure faster? So these are a couple of different ways in which machine learning and sort of existing physics and engineering models have been integrated together. So this is sort of the first tier one here was take machine learning, apply it to a physics model. The other way in which these two areas have been bridged has been bringing constraints from physics into machine learning models. So there have been a couple of works, for example, that have tried to combine deep learning and an optimization concept called Lagrangian duality. There have also been a couple of different papers that have taken power system optimization problems and actually stuck them into deep neural networks. So I'm going to go into that one in a little more detail. So yeah, hopefully we'll get a little more into that. And then the last kind of area here is in terms of embedding robustness constraints into machine learning models. So places where we know that there has to be some kind of provable guarantee on how our machine learning model operates so that it doesn't, again, black out the power system. And there are some works in an area of machine learning called adversarially robust training that deal with this. And there's also a lot of work integrating the area of machine learning, reinforcement learning, as well as traditional control theory work. So that, I realize, is a lot. And for those who would like to dig into these materials further, I can make my slides available. And the reference numbers here are sort of references that are at the end of the slides. But sort of at a high level here, you have machine learning used for engineering brought into the loop of machine learning, and then also work that tries to make machine learning methods certifiably robust. So to just dive in and give one example here of implicit layers in deep learning, so which is one of the areas I talked about earlier. So on the slide here is sort of a kind of, cartoonish representation of a deep neural network. And you might have seen this representation pop up somewhere or the other online. And the basic idea, what this is showing, is that you have some inputs, X, and you're trying to try to figure out, okay, given these inputs X, what should some outputs be, Y hat? So for example, imagine that you're trying to forecast electricity demand. That might be your Y hat. And you might do that on the basis of weather. That would be your X, your input. So you're trying to figure out some way to map from X to Y hat. And in between there, those little traffic light thingies basically create a function. They're basically a bunch of functions composed together. They have some adjustable parameters, and you can adjust those parameters to try to improve your mapping from X to Y hat, to basically improve your forecast of electricity demand, for example. And there are lots of functions that deep learning practitioners will actually use in practice that will kind of, make up these little traffic lights. But what some recent work has done is actually try to expand the notion of what we can actually put into these little traffic lights, what kinds of functions we can actually put in to deep learning methods. And these functions, these custom layers, these custom functions can represent a lot of things. They can represent making your neural network respect some kind of operational constraint, some kind of device constraint. It can reflect a power system optimization problem like AC optimal power flow. And it can represent even rigid body physics, ordinary differential equations, sort of other physical equations that we may care about. And there are, of course, many technical details as to how to create these layers, but sort of the important thing to note is that you can create them, that these layers exist. So my next slide, I'm going to talk a little bit about how we might use these layers. And I apologize, this next slide is the one with the most math on it in this presentation. You don't need to read all of it in order to get it. I'll try to explain it at a high level. So one example application that you can kind of do using these kinds of custom layers in neural networks is provably robust power system control. So the idea is basically, if we have some idea of what the dynamics of our electric power system look like, maybe with some model of uncertainty over those dynamics, we can come up with some potential function that basically tells us how we, what kinds of actions we can take on the system that are safe at any time. Then what we can say is, and this is sort of the math that you can definitely ignore, but feel free to take a look if you are, in this area. Sort of given a current state of the system we're currently at, we can figure out what is the set of actions that is safe for us to take under some notion of robustness. What is the set of actions we can actually take that won't destabilize our underlying power system? And again, feel free to ignore the details there. And then what we can do, and this sort of purple triangle represents this set of safe actions that we can take at a given time. Sort of this, what we can do is we can say, well, if we have a neural network, if it proposes some action we can take, we can then project that action onto the safe set of actions. And then overall, the action that our neural network proposes will be robust. And sort of the neural network that does this looks something like this. You have sort of the generic traffic light thingy before, so some kind of generic neural network that is taking in some inputs and outputting some action that you can take on your power system, for example, charging a battery. And that's what that U tilde green variable is. And then you take that initially proposed action, you project it onto your safe set of actions, and you get your final action that you hat out. So again, if not all the details of that were clear, that's totally fine. But the basic idea is that by kind of creating these kinds of building blocks that represent, constraints or optimization problems or things that we care about from the power system's perspective, we can then stick those building blocks into neural networks. And then as a result, sort of make those neural networks more aware of the kinds of physics and hard constraints that need to be satisfied on the electric power system. And these are some results, but basically the upshot is by doing the method I just talked about, we are able to create a neural network method that performs very well, but doesn't get destabilized by various kinds of disturbances on the power grid. Okay. So that was a whirlwind tour of sort of ways in which machine learning and physics and hard constraints can be integrated together. The next area here I'm going to talk about is kind of making machine learning models sort of more ready to be both integrated with regulatory requirements and sort of play nicely with human users. So we often talk about interpretability in the context of electric power systems. So for example, if I have an electricity demand forecast and something goes wrong on the electricity system, I may need to explain to my regulator why, I had some kind of blackout on my system. And that might involve then asking the question of, well, why was my electricity forecast wrong? And machine learning methods can often, there are some kinds of machine learning methods that can provide explanations as to, why they might have generated a particular forecast or made a particular prediction. And there are others, black box models, that can't necessarily do that. And so there's a lot of sort of work in the machine learning community to ask the question of how can we create fundamentally interpretable models? Now, a challenge there is, though, that a model's interpretation is only useful if it's actually the interpretation that is useful to us. This is kind of tautological, but basically there's no such thing as a generic notion of interpretability. Usually there's some reason that we want something to be interpretable. There's some time at which we want something to be interpretable. There's something we're trying to do with that particular explanation of a model's outputs. And so without sort of without sort of defining those energy system specific notions of when we need interpretability, for what purpose, and sort of what is an acceptable notion of interpretability to serve that purpose, it's then actually not possible to develop machine learning methods that actually do that well for us. So this is sort of a kind of ask to both the machine learning community and the power systems community to say, look, we really need to work together here to develop specifications of when and where we need interpretability, so that the machine learning practitioners can then actually develop methods that meet that criteria. Another area of importance here is uncertainty-aware machine learning. So machine learning methods that can actually give you some notion of how certain they are about their predictions. So again, thinking of demand forecasting, when I give you a particular demand forecast, am I certain about that demand forecast, or am I not necessarily very certain about that forecast in a particular hour? And that will sort of change potentially the decision that's made on the basis of that forecast. And again, there's just sort of some questions here about what kinds of uncertainty do we actually want to measure. So for example, is there uncertainty in the underlying data that we want the model to be able to take into account? Or are we certain about the data that we're giving the model, and it's more about understanding, if the model is uncertain about its own predictions given certain data? So again, there's sort of a lot of interfacing to be done here between the machine learning and power systems communities to better define, what kinds of uncertainty do we actually want to quantify in order to develop methods that can actually report on that kind of uncertainty. And then finally, there's been some work that has tried to kind of embed information about how its outputs will be used into the way it actually creates predictions. So for example, demand forecasting algorithms that, knowing that their outputs are going to be used for something like AC optimal power flow or economic dispatch or some kind of power system optimization model, actually take that into account in order to create better predictions. And so really briefly, going into that notion, in general, when we create, forecasting models in machine learning, we tend to just create models that optimize for accuracy. So for example, a demand forecasting model that's as accurate as possible. And then we hand it off to, a power system operator and say, hey, use this model, use it to operate your system. And so basically there are some issues with that. So for example, if a demand forecasting model, for example, overpredicts what the demand will be in the future, or if it underpredicts what demand will be in the future, that has different implications for how much either extra or too little power is procured, what the costs of that are, what the emissions implications of that are. And yet a demand forecasting model that just optimizes for accuracy misses those nuances. It thinks an underprediction of a certain amount and an overprediction of a certain amount are exactly the same. And so there's been some work that basically says, can we try to make our demand forecasting model cognizant of how exactly its forecasts will be used? I'm just going to skip that. Yeah, so basically the idea is if you have some demand forecasting model that is taking in some information about past demand, weather, time, etc., and it's making some predictions of future electricity demand, it also has some notion of, if I make a prediction of electricity demand, what will the electricity generation schedule made on that basis actually look like? And now, instead of just trying to optimize for the accuracy of the prediction, instead it tries to optimize for the quality of the power generation schedule that was generated on behalf of that, on the basis of that forecast. And so the model here looks something like this. You again have some generic traffic lighty thing at the beginning, some generic neural network that's taking in some inputs and outputting some demand forecast y hat. That demand forecast goes into a power system optimization model, which then puts out a power system generation schedule. And then we try to understand how good is that power system generation schedule when evaluated on the actual demand that we see in the future. And the upshot here is that kind of taking this kind of decision-driven approach can actually lead to up to even 40% improvements in the costs of actually scheduling power generation on the grid, in a very synthetic example on the slide. And then last, very briefly, I want to talk about this issue of distribution shift. So again, distribution shift is the kind of issue we face when the data that we train or our machine learning model on is different than the environment in which we actually evaluate it on. So again, think about creating a demand forecasting model before COVID and trying to apply that model during COVID. That wouldn't work because the underlying reality of the system has actually changed. And there are a couple of kinds of distribution shift that I think we're very likely to face in the near term. So one of them is due to climate change. I think, for example, the ERCOT blackouts are a great example of how we definitely need to be thinking about how demand patterns, for example, will change due to climate. And another example, and another one here is just thinking about the differences in data availability between different entities within a particular country across geographical contexts and needing to develop methods that sort of work at some level across these different contexts. And so there has been a lot of work in areas such as transfer learning, domain adaptation. I'm just throwing out some buzzwords here in case you want to look them up later. And then low resource learning, basically ways to learn with small amounts of data that become very important in this particular context. So the last thing I'll kind of mention, so those were sort of 3 research foci that I think are really important for the machine learning community to focus on. So that's physics, interpretability, and distribution shift. But then the last thing I want to mention is that, it's very easy to develop machine learning models in some kind of, silo and within research, and it's often very hard to test them out in deployment. And there are a couple of reasons for that. So one of them is data availability. Of course, data is often distributed, private, not necessarily properly licensed. And so even if there's an open data portal, you're not always sure, can I use this to actually publish research or, create a deployable product? And I think saliently, as we think about multidisciplinary research problems, this data is not often labeled alongside or annotated with clear use cases. I think it takes a real expert to completely understand what is in this data set, what can I do with it, what kinds of problems does it actually help me to address. And so I think these kinds of things, of this sort of clean data, annotated, licensed, will be really crucial to sort of getting a larger base of people who are working in these areas. And then also various kinds of more generic requests around open data initiatives and also sort of data literacy and capacity among a wide range of stakeholders. Test beds and demonstration projects. So as I mentioned earlier, a lot of the kind of areas I'm talking about here are very motivated by those workflows where machine learning has to be integrated with legacy software, for example. And yet, there aren't generally ways in which to actually test this out. If you want to understand whether your machine learning model can actually help speed up a power system dispatch model that's being used by some kind of electricity system operator, you don't really have any way to do that. And so there needs to be sort of some kind of better way to try to actually test out some of these methods that we are developing in academia. And one way forward here is through competition. So for example, the Learning to Run a Power Network Challenge, which EPRI has been involved in, which RTE France has been involved in, among others, where they are sort of starting to put out, these are problems and these are, sample electricity system simulation environments that start to represent what we actually need, develop methods, test them out there. And they're creating a multi-stage competition where the infrastructure is more mature at every single stage. So that's kind of one way in which this kind of work can be promoted. And then the last I'll say is sort of opportunities for knowledge transfer and talent sharing. I think we can talk about all day long, I in the electricity sector need this particular, I have this particular need, or I in academia have this particular method. But I think until we really are embedded in each other's worlds in a more meaningful way, I think a lot of these, collaborations and ways forward won't really emerge. So basically, I think there's a real need to develop, fellowship programs, placement programs, in-residence programs where, for example, folks from academia spend a substantive amount of time in a utility or an electricity system operator or so forth, in order to actually both gain insight into what the on-the-ground challenges are, but then likewise be able to bring their sort of innovation expertise into the loop in order to kind of recommend places where there could be either room for innovation or it would be useful to collect data in order to make space for that innovation and so forth. And more generally, this leads to a kind of just stronger need for various kinds of academia industry partnerships. So with that, I just wanted to close and quickly summarize. So I talked about some key foci, key areas of focus for machine learning methods to be developed. So one of them is, again, physics. One of them is interacting with users and regulatory requirements, which generally means interpretability and uncertainty quantification. And also the ability to deal with sort of differences in data distributions across time and across different entities. There are lots of needs in terms of research deployment, so open and clearly contextualized data, test beds, and various ways for knowledge transfer and talent sharing. And that's it. I would love to take questions if we still have time. And also, please do feel free to reach out to me via email. My email is on the slide. Thank you.
It was a fascinating talk, not just the work that you're doing, but also, more generally, academia, sort of the different areas within the machine learning community. I think that was super interesting to get that perspective. I really liked it. So I'm looking at the time. We're a bit over half time. So I actually had a lot of questions on your site. So I definitely will follow up by email. I know there was one in the chat. Let's keep that maybe for now. I'm going to go over to the LA team to make sure we keep enough time for them, and then if we have time in the end, maybe we'll have a discussion then, or our breakout session. So from Los Angeles Department of Water and Power, we have with us Maria, Jay, George, and Hassan. So Maria is the manager of corporate sustainability programs. Jay is the manager of integrated resources planning. George is from the Financial Services Executive Office, and Hassan is the manager of the demand response program. And so I think today the LA team, the LA.DWP team, will be talking not only about LA's goals for decarbonization and electrification, but also a recent study by NREL that LA.DWP did in partnership with NREL to look at plans for the next decade. So I actually think this is going to be a very interesting counterpart to what Priya just gave us. Sort of more of the story from the industry, and if you can, and we'll talk more about this in breakout session. But I think one of the things that we're also on the academic side trying to hear from sessions like these is what are things that are difficult. Not only what are your plans, what are you trying to do, what are your goals, but what are things you can't do. Okay, with that, I'll stop and over to Maria.
Thank you so much. And thanks for introducing my esteemed colleagues here who will be following me shortly. So again, I'm Maria Sison Roses, Manager of Corporate Sustainability Programs at LA.DWP. I'm going to be followed by Jay Lim, the Manager of LA.DWP's Integrated Resource Planning. Jay will talk about the power system goals and potential AI opportunities. And then he'll be followed next by George Chen from our Financial Services Executive Office. George will provide some thoughts on how AI can help further LA.DWP's electrification of transportation program. And then last but not least, we'll have Hassan Motalebi. Hassan is the manager of LA.DWP's demand response program. And Hassan will talk about how AI can help play a role in expanding his program. So if we can go on to the next slide, I'll provide a brief overview of LA.DWP for those who may not be as familiar. So LA.DWP was established over 100 years ago, first to deliver water in 1902, and then a decade later to deliver electricity in 1916. The interesting thing about this over a century history of LA.DWP is that one realizes it's really just within the last decade that the transformation in terms of the sources of fuel for LA.DWP has taken place. And you'll hear more about that from Jay. LA.DWP is the largest municipal utility in the country. Our service territory covers LA's 465 square miles. LA has about 4 million residents, with LA being the second most populous city in the US. We have about 1.6 million electric customers and about 680,000 water customers. Let's stay on this slide, please. And I just want to share a few more thoughts. So LA is a very diverse city, regionally, culturally, economically, and socially. We have a very diverse customer base. In fact, nearly 40% of LA's residents are foreign born. Over 185 languages are spoken. Sometimes I read over 200. We have our fair share of disadvantaged and underserved customer segments, lots of multifamily residents and apartment dwellers. And that is why equity plays a huge role in our efforts. LADWP also has affordability as part of its mission. And that's why we invest so heavily in energy efficiency to help our customers increase the efficiency of their homes, reduce their energy use, reduce their water use, and therefore lower their bills, the energy burden. And at the same time, LADWP invests in innovation and new technologies. And this is where I think AI can really play a huge role in asking the right questions, helping us to find the answers to the questions such as how do we better understand our customers and their behaviors? How can we engage our customers in our programs? How do we bring them along in our own decarbonization and electrification efforts, regardless of where they live and what their zip code is? And how can we use AI to be able to better tell that story and highlight the shared values and needs of cleaner air, sustainability, and resiliency? So if we can go to the next slide. This is a slide of LADWP's 5-0 goals as lifted from LA's Green New Deal, which is our North Star. So starting off with a zero carbon grid, zero carbon buildings, zero carbon transportation, zero waste, and zero wasted water. Obviously, LADWP plays a key role in these efforts, and our plans, our programs, and our efforts are all geared toward achieving these goals. So I'm going to pause right there and pass it on to Jay to talk about our power system goals and how AI can play a lot of opportunities. Thank you.
All right, next slide, please. All right, thank you, Maria. So good morning. My name is Jay Lim, and I'm the manager of LADWP's Integrated Resource Planning. Recently, LADWP completed a multi-year study called the LA 100 study. This was in partnership with the National Renewable Energy Laboratory to determine the investments needed to achieve 100% renewable goal by 2045 or earlier. The LA 100 study was the most comprehensive, detailed study to model an entirely renewable-based power system as complex as LA's, and NREL ran millions of simulations to evaluate a range of future scenarios for how LADWP's power system could evolve to 100% clean energy future while also maintaining reliable power for its LA customers. The LA 100 study extensively utilized artificial intelligence, including a supercomputer at NREL and dozens of different models to forecast demand for electricity, optimize resources, simulate extreme events for reliability, analyze impacts on jobs, air quality, local economy, and environmental justice, and determine investment costs. Following the conclusion of the LA 100 study, on April 19, 2021, the City of Los Angeles Mayor Eric Garcetti committed LADWP to provide 80% renewables by 2030 and commit to 100% carbon-free by 2035, 10 years ahead of President Biden's vision. And this would be utilizing LA 100's most aggressive blueprint as the scenario moving forward, called the early and no biofuel scenario. In following the mayor's directive, LADWP has conducted internal analysis in parallel using a production cost model to identify near-term actions to achieve these goals. Each of these elements includes opportunities for artificial intelligence. The first is 80% renewable by 2030 and 90% carbon-free by 2030. The power system grid will need to evolve from a system that is predominantly thermal resources to a system dominated by intermittent and variable renewables that's firmed with energy storage. In order to get there, LADWP will be adding approximately 3,000 megawatts of new renewable energy projects by 2030. And artificial intelligence can help LADWP optimize operations of the grid. Next is accelerating local transmission projects. Since transmission requires a long lead time to upgrade and construct, LADWP has the opportunity through AI to maximize the transmission bandwidth to take advantage of existing transmission assets 24/7. Third is transforming local generation. LADWP will be decarbonizing its local generation, and AI can help assist with the local generation fleet to help back up renewables and optimize system costs. Fourth is accelerating energy storage. Over 1,000 megawatts of energy storage have been identified that will need to be deployed by 2030 to address once-through cooling thermal retirements, and AI can help optimize its usage for reliability, frequency control, and avoiding curtailment. Last, distributed energy resources will play a key role in LADWP's 100% carbon-free future, where LADWP's distribution grid will evolve from one-way flows to two-way flows, allowing customers to participate in various programs. Programs such as local solar, demand response, energy efficiency, and transportation electrification can be both controlled and optimized by AI. Machine learning methods can help forecast and predict customer adoption rates. Next slide, please. So what are the outcomes of all of these elements? LADWP will be transforming its grid from 38% renewable today in 2020 to 80% by 2030, while also significantly reducing natural gas usage to drive emissions down. One factor to point out here is that although LADWP's nuclear asset in Palo Verde is fixed at 380 megawatts, the percentage of sales will reduce from 14% today to 10% from 2019 to 2030. And this is driven by primarily the growth from transportation electrification. So now I want to turn it over to my colleague, George Chen, who will talk about that further.
Okay, thank you, Jay. And I'm going to talk about one of the challenges we have. Actually, that's a massive challenge. LA will adopt a lot of electrical vehicles, and we currently have 59,000 electrical vehicles, residential electrical vehicles. And by 2030, we're looking at 300,000 electrical vehicles, and that's just a low number. I mean, the high number is going to be double that amount. And so let's look at the the engineering side of these. Each electrical vehicle takes about 6 kilowatts to charge. That's the average power. The maximum power requirement is 20 kW. So we just use the 6 kW. And use that number, if you time 300,000, meaning that if all 300,000 electrical vehicles turn on charge at the same time, it will require 1,800 megawatts. So you said, oh, it's 1,800 megawatts. How much is that? The entire LA, Los Angeles area, the peak usage, the highest point is only 6,000. So it's about 30% of our peak load if we don't manage them charging, and it will cause a lot of the power requirement to our system. And just to build those power capacity standby for the EV come online will cost us 180 million a year. So it's a lot of investment. So our rate's gonna go high, much higher if we don't manage it correctly. And also that will put a lot of stress on our the distribution system, because the insulation, everything else is suddenly all this power coming on. It's gonna be require a lot of capacity. in our distribution system, transmission system, as well as a generation system. So that's going to cost a lot of money. It's going to huge financial impact to the department if we don't manage them well. Next slide, please. So we look at the potential solution, right? That we previous presenter, talk about the solutions. I think, well, that's pretty familiar, and we have data. We know on the top row, we kind of draw a little bit of the diagram, thinking that could be the solution. We have the available generation. We know that every hours, what kind of generation standby we have it. And we also have a load forecast, right? Daily load forecast, annual load forecast, and we also have temperature forecast. So all this information can also incorporate into the system. And also very importantly, right, customer gonna be making their decisions, charging or not charging based on rates. So we also have a rates information. And more importantly, the current load, what's current customer use, what's our current power output, and so we can have that information available. So all this can feed into the AI system, and at the bottom row you can see all the different electrical vehicles. So we can have the AI decide how to schedule them based on geography difference, and also depends on available the load. So to do that, we need all different sections of people working together and create a standard, right? We have to have what's the optimum data inputs. So the top row, is that all the information do we need, or we need more? So we have to establish that standard. And so also we need the AI community help us to get the algorithm and help us to test these systems. And also we need the communication protocols and the control data storage standards developed. And on the utility side, we can provide incentives, right? Customers say, why I need to let you control the charging time. We say, okay, I can help you to lower your rate. And also we can provide rebates for those controllable charger, and we pay a little bit more. I think maybe around $300. You can get some better version. And also we can use the charger meter as our utility meter to do the billing calculation. So all this has to be developed, and we need to have a nationwide standard. How can we incorporate the EV and the great integration using AI technology? Next slide, please. And so we're gonna look at there's also financial benefit for the customer, right? So let's assume the EV charger requires power 250 kWh per month, and we assume EV charging rate is 30 cents. So that's just assumption number, but our much lower. But I just say, okay, nationally maybe we use the 30 as just the base to have a discussion here. And then that multiply annual charging bill is about $900. But if the customer allow us to manage the charging and to do all these demand response kind of different programs, and we can just charge them about 20 cents, and the customer annual bill will be around $600. So they can save about $300 annually. So I mean, we talk about there's enough incentive for the utility to invest in this AI technology. At the same time, customer has the benefit too. So, and also we'll manage our load better. Like Jim mentioned, without the AI, we cannot reach the 100% renewable cost effectively. So I'm gonna hand this to Hassan. He's gonna go over the more detail on our demand response programs. Thank you.
Thank you, George. Should be afternoon there. Good afternoon. My name is Hassan Motalibi. and I'm the program manager for demand response at LADWP. And I've been doing so since 2014 when we first started launching our demand response programs. Currently, we have two types of DR programs at DWP. Both of them are incentive-based. As you know, DR programs could be either incentive-based or price-based or both, combination of both. So far, we've been implementing an incentive-based DR program, and with application of AI, we're hoping that we can start exploring the price-based demand response program by having better tools of estimating the load and also the program participants' performance during DR events based on historical data with AI. If we can accurately estimate or basically forecast how different segments of customers would perform in the future under different conditions for DR, temperature being one of those. With the commercial DR, as I said, we started in 2015. We had a pilot back in 2015. Our portfolio was about 5.6 megawatts. And over the past 5 years, as you see across the board there, each year, we've increased it to 30 in 2016, 24 in 2017, and 2018 also went down a little bit, but we came back up in 2019 to about 37 megawatts. And in 2020, because of COVID and the shutdowns, naturally the baseline went down, and we had business closures in LA. They were at about 25% capacity, so our portfolio dropped accordingly to 28. And now we're back up to 40 megawatts again. Well, we expect to get there by 58 participants. We started with 28 with our pilot. We're at 58 major customers participating in the program. In terms of savings, that has increased consistently over the past years. We started with about 112 megawatt hours in 2015. And over the years, we've gone to 480, 522, 445, 443, 658. And this year, we'll probably be in the range of 700 megawatt hours of savings. In terms of events, those very unique days that we had to call on our customers to curtail their peak load. In 2015, we had 5 events. In 2016, we had only 4 events. In 2017, we had 6, 18, 5. In 2019, only 3 events. And in 2020, with the heat waves we had in LA, we had over 8 events, and the customers performed consistently according to their commitment. Now, with this program, as I said, is incentive-based. We have 2 tiers of incentives, which are valued depending on which program the customer selects. We have a 24-hour advance notice program, and we also have a 2-hour advance notice. We offer more incentives for 2-hour advance notice and a little less for 24. On top of that, this is the capacity incentive we provide for the capacity. We also have energy incentives that we just count the kilowatt hours a customer curtails or saves, and we provide that to them in the form of a check. Next slide, please. Yes, that was a commercial DR. It's been in effect since 2015. We do plan to grow that at the rate of about 15 megawatts each year. We're hoping to hit numbers close to 200 megawatts or so by 2030 and beyond. Now, we also have a residential demand response program, which is fully automated. We launched this in 2020. We finished the season with almost 18,000 customers on the residential side. And these 18,000 customers enrolled about 25,000 devices. These are thermostats controlling the cooling load. We offer rebates, one-time rebate to purchase a thermostat and join the program, and also annual incentives to encourage the customer to stay on the program and continue with energy savings. In 2020, the season we just ended, we had about 10 events. Collectively, our customers, residential customers, were able to curtail about 80 megawatts. an average of 8.25 megawatt per event over the 10 events. The total energy savings from the residential customers for the first year was about 212 megawatt hours. And the incentives and rebates we've paid for this program so far is in the neighborhood of $3.5 million. Now, this year, our participation has increased quite a bit. We've gone from 18,000 devices at the end of last year, which is, by the way, the season runs between October 1st to December 31st. We ended the season with about 18,000 devices. Today, we're at about 27, almost 28,000 devices. We're expecting to hit about 30,000 devices by early summer, and perhaps by midsummer to the end of the season, near October, in September, October, we should be at about 35,000 to 36,000 devices. These devices will give us, collectively, will give us a value of about 25 megawatts. That's our goal for this year, or at the latest by early next summer. And we do intend to grow this program to scale it up by about 10 megawatts each year. So combined commercial and residential, we're talking about 25 megawatts. In terms of scaling up, 15 from commercial, 10 from residential. Now, this also, as I said, this is also incentive-based. None of these programs are price-based. Now, to start exploring critical peak pricing, time of use, that's when we need AI to provide better forecasting of the load. And in addition to that, we're hoping to get better forecasting on the performance of customers, not just one customer, a segment of customers, so we can start tiering our incentives and pricing. Now we have 2 tiers for commercial and just 1 for residential. At that point, maybe our, budget folks like George could start, tiering the rates more often. I mean, with having more tiers for the rates. I don't want to talk for that program, but with DR, we can definitely start introducing different types of incentives based on, for example, based on customers' performance. Say customers that perform up to 100 kW could get 1 tier, then from 100 kW to 250, that would go into another tier, 250 to 500, so on and so forth. The more they perform, we can incentivize them more to encourage them to join the program and participate in it. Now, how does AI come in? Mainly with forecasting, both in terms of load, peak load, and also customers' performance during certain DR events. For now, they're all, we call these events when the temperature is high, as we saw in 2020. We had 8 events with the heat waves. And with more data, real-time data, perhaps we can bring in other factors in determining the best days for calling DR to better optimize the incentives with the performances. And that concludes my presentation. Who's next? Okay, thank you.
Yep. So I think we have 2 minutes late. 2 minutes left, and I guess so we won't have time for questions for the LADW team, P team either. So I think we'll push that to the breakout. So I encourage everyone to come back for the breakout session. And I guess there are a couple of things I already know we want to talk about. Thanks for both both presenters. I was very interested to hear about both topics, very different topics, but I think very complementary. And I already know at least 2 threads that I hope we can talk about in the breakout session. One, and I guess jumping off what Hassan was just talking about, different how do different types of demand response perform, and what's the uncertainty related to that. That's one of the things that Priya talked about. And I think that's one of the challenges where on the academic side we see tools that maybe could help. And I think it's also something that changes a lot if you're looking at a CNI demand response program versus a residential demand response program. In one case, you have few customers, and you can kind of build a relationship with them. On the other one, you have hundreds of thousands, possibly millions of customers, and you want to have some sort of guarantee on how they're going to perform. So that's one of the threads I'd like to talk about. Another one that I was thinking of just now, and I definitely think there will be more. Another one is infrastructure design under uncertainty. If I think back to what Jay was talking about in the beginning, integrated resource planning, sort of coupling that with what Priya was talking about on what Priya was calling the distribution shift. How do we build these future energy systems given that the information we have today may not be reliable to think about the weather patterns, the weather, what's the distribution for temperature in 20 years? That may no longer be accurate. So with that, I think we're at time. So Hannah, I think you're heading us back to the break.
Awesome. Yeah, thank you so much, Jacques. And thank you to the rest of the team. That was really great. I know that there was a lot of questions that we didn't get to address from the audience, but I just want to let you guys know we're going to go to a 30-minute break right now. We will be back at 3 p.m. Eastern. What we need to do, we're going to be in breakout sessions. So Jacques kind of mentioned a lot of the topics that we're going to cover. Those 3 breakout sessions are going to be decarbonization, demand response, and customer engagement. That's session 1. Session 2 is asset management, and session 3 will be resiliency and outage optimization. So we'll go on our 30-minute break. We'll have the music playing in the background just like normal. When you come back here, you'll see a slide. It's going to give you directions on what to do. There are some links in the agenda just below the video screen that will take you to a breakout. And if you want to switch between breakouts throughout the breakout session time, that's absolutely fine. You just need to exit out and click on a new link. All right, guys, that's enough for today. I'm going to stop here. We'll go to break, and then we will see you guys in the breakout rooms. Thank you very much.